So welcome to the today's lab. Okay, this is the lab number 5, right? Okay. Today we are going to look at the modeling of different combinational circuits using structural modeling. Okay, modeling of uh, okay, let me write in this way only. Modeling using structural model. Okay. So the already we have modeled different kind of things, right? Okay. We started off modeling of half-adder, full-adder. Okay, and 2x1 multiplexer and decoder that we have seen. Okay, these are the fundamental building blocks that we have seen previously. By using these particular components, we are going to construct some bigger combinational circuits. Okay, for example, if I want to write the I want to write a Verilog program for the first one is 4-bit adder. Okay, 4-bit adder, but by using full adders, by using 1-bit adder. 1-bit adder in the sense it is a full adder simply. Okay, I want to construct a 4-bit adder by using 1-bit adder or full adder. Okay, that is the one thing. The second one is, let us write 8x1 multiplexer, 8x1 mux using 2x1 multiplexer. Already we have modeled the 2x1 multiplexer, how to construct 8x1 multiplexer by using that one, and we want to model that one. Okay, and similarly, we want to construct 3x8 decoder using 2x4 decoder. Okay, so therefore, if you want to model something based on the basic components like half adder, full adder, decoder, to construct a bigger combination circuits like 4-bit adder, 8x1 multiplexer, 3x8 decoders by using the fundamental components, then definitely we have to use the structural modeling. Okay, why? Because we have already defined what is a decoder, what is a multiplexer, what is a full adder. This we can call according to the 8x1 multiplexer, according to the 4-bit adder, according to the 3x8 decoder. Okay, so let us take first example. Okay, how to construct a 4-bit adder. Our requirement is that we have to use the structural modeling. Okay, so what is the top level view of this 4-bit adder? How many input it will take, how many outputs it will give you? Okay, I think it's not good. Okay, how many input to 4-bit adder means? Let us consider A is one operand. What is its side? 4-bit size. Okay. And similarly, we have to take B is also one input signal. Its size is also 4-bit size. Okay. And there is a one carry in signal. Let me consider this a carry in signal. It is a single bit size. Similarly, we have a sum signal. It is also have 4-bit size. We have a carry out signal, C out. It should be 1-bit size. So this is what the top level view of your 4-bit adder, right? Okay, 4-bit adder means two 4-bit operands need to be added, and it should produce some signal and carry signal. All right? Okay. Now the question is, what is inside of it? That's the what important. Okay. So according to the specification, we have to construct this one by using the full address. Okay. So now tell me what you have to do it. For example, A is actually assume that, for example, A3, A2, A1, A0. It's a 4-bit number, 4-bit number. B is also 4-bit, B3, B2, B1, B0. Okay. And of course, there is a CN signal. Let me consider the CN here. Okay. Let me consider CN directly. Now I want to add these things, right? I should add these things. What should I get? Okay. So definitely a bit by bit addition that we do, right? Okay. First, this bit we'll consider, and second, this bit will consider, and third, this bit will consider. All these three bits will be added. That is simply full adder is sufficient, right? We have seen what is the full adder. A bit, B bit, and CN bit is there. And then we have to add all these things which will produce sum and carry. Okay. So assume that it's producing the sum is S0 and it is also producing C0 is a carry. Okay. Carry will be forwarded to the next stage. Simple addition. Similarly, we have to add, therefore, we need to have one adder is required here. A full adder is required here, right? Similarly, if you want to add all this A1, B1, C0, again, what we need, some other full adder is there. So it will produce the sum signal one and C1, C or carry signal of that one. So here also one full adder is required. Again, if you want to add these three bits, for example, again, one full adder is required. It will produce S2 and this is C2. Okay. And again, if you want to add A3, B3 and C2, I need to have another full adder and it will produce S3 and carry will be generated. This is what the C out, for example. Okay. Is it clear to everyone? Okay. Therefore, how many full adders are required to construct a 4-bit adder? 4 full adders are required. For example, 32-bit adder is required, for example. Then how many 1-bit adders are required? 32 full adders are required. Am I clear? Okay. So since we have taken a simple example 4-bit adder, we'll do the 4-bit adder. This is similar to that. We can extend this one to the 32-bit also. Okay, fine. Now we know that what is the external view, what is its operation, how it will be constructed. Let us take the simple diagram for this. Okay, as we know that we need to have 4 1-bit full adders. This is the one. This is the second one. Third one. And this is the fourth one. Okay. So let me consider this is a FA naught. Okay, since all are 4-bit adders only, that let me take this is the FA naught, the first adder. This is the second full adder. This is the third full adder. This is the fourth full adder. See, normally the naming, the number system will start with 0. Since we are talking about the binary number system, we'll start with the lowest number must be 0, highest number can be anything. Okay. Not that we want to start with 1 and 2 and something. Okay. This is the usual practice. Okay. Now, what is the input for this one? So I have used the vector notation. Can you clearly observe this one? It's a vector notation I'm using, right? Okay. That means that I have to use here. Of course, there is a CN signal. There is a CAN signal. And one input is A of 0. Next, this is B of 0. The first bit of A and first bit of B, and add this one to the CAN. So it will produce what? It will produce S naught. Oh, sorry, it will produce in a vector form. We have to represent it as S of 0. Agreed? Okay. So what it will produce now? So this produce some carry signal. Let me consider this is a C0. Okay, because this intermediate line is also I want to write it as a vector notation. Okay, what is the size of this carry signal inside of the module? Inside of the module, you can see it's a 3 bits. 3 bits are required for this one. Okay, we will talk about that one while you are writing. Similarly, we have to write A of second bit of the A, second bit of B, and the carry is already available, and it should produce S of 1. And now again, it will produce the C of 1. Okay. Now, with this, we need to add the third bit of A and third bit of B. And it will produce S of 2. Third bit it will produce. It will also produce the carry information C of 2. With this carry and the fourth bit of A, that is A of 3 and B of 3 will be added, and it will produce S of S3. And it will produce C out. It will produce C out. Okay, this is what inside of your 4+1, sorry, 4-bit adder. So this is the design part actually, right? By using the 1-bit adder, I'm able to realize 4-bit adder. Okay. So you know the structure, okay? And we need to write a structural modeling. Okay. Here, can we call this as a gate level modeling? No, it is not a gate level. We cannot call it as a gate level modeling because we have not seen any kind of gate, because it's not the lowest level of abstraction we are not using here, because full adder is already defined with the gates. Therefore, it is a subcomponent here. Okay. So therefore, normally it is called a structural programming. Okay. Now, in a previous example, in a previous class, in a previous lab, we have already seen how to realize the full adder, right? Okay. Now it is a multiplexer. It is a already have defined, okay, half adder and full adder. Okay, no, not a problem. Already have I not defined the full adder directly or somewhere else? Okay, this is only half adders only I have done, I guess, right? Okay, no problem. This is the full adder is already available in the form of structural modeling. We take that full adder directly. Okay. Okay. What is the name of this full adder that I have taken? Okay, this is what I have considered, right? Okay, let me copy this one. Let me copy this. Copy. Okay, so I want to keep it somewhere here. Okay, let us start a Verilog program for this now. So this is the module I'm taking. This is structural modeling of full address. Actually, also a structural modeling, which is implemented by using the half address. Okay, this is already tested thoroughly. Okay, by using some kind of the test bench also. It is perfectly working now. Okay, just now once it is working, we have to take and we have to write for the 4-bit adder. Okay, now how do we start the 4-bit adder? Let us start in this way. Module add underscore 4-bit, something like this I have written. Okay, underscore structural modeling SM. This is for my identification purpose. I have written this. This is the way that I have written the name of my module. Okay, what are the variables I'm using here? Okay, let me better. I can have to take this particular thing and keep it here so that I'm able to see this one, and I'm going to write everything. I'm using the variable A, right? And I'm using the variable B, and I'm using the variable CAN, and I'm using the variable sum. I'm using the variable Cout. Okay, and semicolon. Please remember that one. In my example, okay, the way how I have written the C here, capital C and small in I have written, but actually it's not the capital C. This is small c. All are capital, small, lowercase letters only, right? We can write it for the uppercase letters also, because all the time we have to make the first letters capital and then write the small letters. We don't want to do it. Write it. Everything is on the capital, small letters. This better. Okay. Otherwise, sometimes we mismatch that one. If you're using the capital C and small can, and somewhere in the program you write a small can or all are uppercase letters, they create a lot of problems because they are not recognized. Okay, they cannot recognize it. Okay, so I can keep it like this. Okay. Now, what are the variables that I have used for what purpose I'm using A, B, and C for the input purpose, right? We write the input. What is the size of the inputs? A and B are 4-bit size of A, comma B. Okay, A, B are 4-bit size. And another input is this is a different size. That's the reason why I have to write the different input keyword. And we need to write CIN. Okay. Okay. Now, what about next one? So, and sum and Cout are available. The variables are available. I'm going to use that one for the purpose of output. Okay. Output sum. I'm so sorry. What is its size? Yes, very good. 3 down to 0. Sum. And another output is also required for single output. Output Cout. Okay. We have declared all the variables according to their purpose. Now I need to call. How many times I need to call this ladder? 4 times I need to call. Okay. Anyway, I have defined this one previously. I'm just copy and paste that one. Okay. If you're not able to, if you're not model this particular component, then definitely we should not use it. Okay. Assuming that I have modeled this FA underscore SM previously. Right. Now, what is this name of this module? What is the name of this module? The name of this module is FA naught. Okay. FA naught. Okay. Therefore, this is what I'm talking about. Okay. Okay. Better I can take this one also somewhere here. I want to copy here. Copy that one. and paste it somewhere here. Okay, this is the first FA naught is completed, right? Okay, this is what FA naught. Now I need to take how many times? 3 times. First I want to copy. Okay, better I want to. Actually, the A of this one is connected to what? This A must be connected to what? This A must be connected to A of 0. This B is connected to B of 0. This CN is connected to this CAN. Of course, this CN. Okay. This sum is connected to what? S of 0. This C out is connected to this C of 0. Okay. So we have to do that one. Okay. Here we can use the farmers and actuals method. Okay. Or otherwise, we can also directly use the same notation. Okay. Let us do in this way. Both I can write. Okay. Farmers and actuals and positions also I can write. Okay. Here, I do. Okay. This A, B, C, and sum and C out. Okay. That is what they have written. Okay. What is the first one? A of 0. What is the second one? B of 0. What is the third one? CAN. What is the fourth one? S of 0. Okay, S of 0 I have written. Okay, not sum here actually I have written. It is S only. Please remember there is an S. Comma C of 0. Okay. So this is the positional way of writing the instantiating the component. Okay, for the sake of simplicity, for the sake of explaining the other way also, what I have done here, let me take this here, this component. For the second one, we would like to write in this way. Okay. Okay. Fine. What is the name of this component? Let us give. Let us give the name of this one is FA1. Okay. Now, A of this one is connected to what? The dot A of available existing the full adder is connected to, I'm so sorry, connected to A1 of the structural modeling full adder, 4-bit adder, comma, B of the full adder is connected to the first bit of second bit of 4-bit adder. Okay. And CAN of full adder is mapped to, the right word is mapped to, what is this one? C of 0. That's what I can say, right? You can observe this one. Therefore, the first A of this one, A of the full adder is connected to what? A of 1. Okay. Next, B of full adder is connected to B1 of 4-bit adder. CN of the full adder is connected to C0 of 4-bit adder. Something like this I have. Okay. And comma, I can write what are the other things? Sum. The sum of this one is mapped to S of 1, comma, dot C out is connected to, of the full adder is connected to C of 1 of the 4-bit adder. So this is how we need to write. This is called formers and actors. Almost this is the way that people, most people will like in this manner only. Sum. Output is mentioned as S. Yeah, S only, S variable only I have written here. So this is actually the full adder that is defined in the previously. This full adder, so the C, small a, small b, small c, and small SOM, small c out is defined in this particular adder. Okay, this particular adder I have mentioned in this way, in this adder. But in this adder, I have mentioned the sum is actually S only. In this adder, S only I have defined. Okay, in this here. Okay, fine. Okay, here is S. Okay. So this way is more suitable to write this down. Please let me know what is the advantage of using this approach. Huh? We can interchange the variables. Okay, that means if you want to use this, for example, this particular one, if you would like to write this some signal at the first place, we can write that in the first place. It doesn't have any problem. Okay. So, but whereas it's not possible that S of 0 is cannot be written at this first place in this particular case, right? Be careful about it. Okay. So since it is this particular approach is taking a lot of course, it's not a lot of time, but we can also do it. But simplicity, I'm simply I'll go and use this particular approach. Okay. Please use this approach for the time being. What are the modifications here? S2. What is the modification here? S3. It is FK3. So what about here? I should remove this one, should be within the brackets. So we should remove all these things. Okay. Please let me know what it is. S1, S2, sorry, A2, B2, C of 1 and 2 and C1, C2. Similarly here, what about this? These are A3, B3, C of, what is this one? C of 2. I think it's not that much. Look great. Let's write a little bit. 3, what is this? 3, 3, 2, 3. This must be C out. This must be C out. And provided we have to write the wires also, right? Okay. Let me write here is a wire. What is the wire size? Wire 2 down to 0 of C. Okay. Wire is 2 down to 0 of C. Finally, end this module. We need to end the module. This is the structural modeling of 4-bit adder. Okay. Right. Now, similarly, can we do it for the 8x1 multiplexer? Shall we go and quickly write the 8x1 multiplexer? How many 2x1 multiplexers are required to realize 8x1 multiplexer? 12. 4. 8x1 multiplexer. That means 8 inputs should be there and 1 output. If you want to select only one output at a time, one input is transfer to output side at a time, then three selection lines are required, right? Okay. So that is actually the input output definition. Okay, let me write the 8+1 multiplexer here. 8+1 multiplexer. Okay. So definitely we should have there is a what is the input size? For example, input is I, for example. If the size of this one should be 8-bit. What is the size of this one selection line? 3-bit size. And output is only 1-bit size. Okay. So the question is how to construct this one. Okay. So as we know very well about this multiplex race, okay. S3 is one input, S2, S1, S0. Okay. If this is the selection line and Y is my output, then if I apply 0, 0, what will happen? I will get output as I0. Okay. If it is 0, 0, 1, I1, 0, 1, 0, I2, 0, 1, 1, I3, 1, 0, 0, I4, 1, 0, 0, 1, 0, 1, I5, 1, 1, 0, I6, 1, 1, 1, I7. Right? Okay. So 2+1 multiplexer can accommodate two inputs at a time. Okay. But how many inputs we have here? 8 inputs. Okay. How many 2+1 multiplexers are required then? 4. Okay. At the first stage, we need to have 4. Right. Here we need to take 4 multiplexers. 4 2+1 multiplexers. 1. Paste here. Paste here. Paste here. Right? Okay. So these are the things. Okay. So anyway, what I'm going to create here now is simply I 0 to 1. Okay. Next year, I 2 to 3. Here, I 4 to 5. Here, I 6 to 7. Okay. So therefore, every multiplexer will accommodate two input signals. Therefore, how many outputs that we are getting here? 1, 2, 3, 4. We have 4 outputs. Now we want only one output. Again, our requirement is that we have to use only, our constraint is that we have to use only 2+1 multiplexer. So then how many 2+1 multiplexer I have to use here? 2, right? So we consider another 2 multiplexers. Okay. Therefore, this is connected here. This is connected here. This is connected here. You're also connected here. And we got 2 output lines. But we want only one output. So that's the reason why again we have to take another multiplexer. Let's connect here. Now we have one output. Did you catch this point? Okay, right. Now the question is how do we select the selection? How do we select? That's not what kind of selection line we have to give for all these three first stage multiplexers, and what kind of selection line we have to give for the second stage of multiplexer. What selection line we have to give for the third stage multiplexer. Okay. Now I want to, for example, if this is the case, look at this one. If this is the case, I naught has to produce. Okay. As we know very well that, okay, let me give this particular numbers here. 0 position 1, 0, 1, 0, and 1. Okay. 0 and 1. What is the 0 and 1? 0 stands for the first variable, 1 stands for second variable. Okay. For example, if you have a multiplexer, something like this, okay. For example, here is A, here is B, for example. So that means 0 stands for first variable, 1 stands for second variable. Okay, if the first variable has to select or second variable has to select, that is decided by the S. If S is equal to 0, means that this is selected. That means that the corresponding related bit will be transferred as an output, right? Similarly, if S is equal to 1, means that the this particular variable one related variable will be considered and it will be transferred to output side. Therefore, it will be now first A will be then second B will come into the picture, right? Similarly, here the first what it has to go, the first bit of this one has to go, and from this one also 0 has to go. Here also 0 1, 0 1, and 0 1. Now you can see 0 0 0. Okay, that means that what should be the here and what should be here. What is your choice? Where we have to give S3, where we have to give S1, where we have to give S0, S2, sorry, S2, S1, S0. Assume that, for example, okay? Assume, for example, here is S3, S1, S0, S1, S2. Assume in this way. Actually, S2 is MSB. According to our notation, S2 is MSB. Okay. Next, S0 is LSB. LSB I have kept it at the first stage and MSB at the last stage at the output side. Now, what will happen if it is all, if it is now, let us assume this is 0, this is 0, this is 0. What will happen? That means since it is this is all, this all first stage multiplexers all are connected to S0. That's the reason why this will be selected, this will be selected, this is also selected, this is also selected, right? The first bit of first variable of all the 4 multiplexers will be selected, right? Now here what will happen? This is also 0. That means this is also selected and this is also selected. Okay. That means that out of this one, which one out of these two, which one will be selected? This is selected. Between these two, which one is selected? This one is selected or this one is selected? This will be selected. Okay. Now, between these two, which will be selected? This is selected or this is selected here? The top one will be selected. That's the reason why it will produce I0, it will be produced. Okay, what is the first one? I0 will be selected as an output. Now, we take the second position, 0, 0, 1, for example. 0, 0, 1. We are expecting that I1 has to come. And then idra aval manaki. Okay na? So what is happening here? 0 means that all zeros will be selected. 0 means that all zeros will be selected, and here for S2 this will be selected. That means what is happening here? It is come from where it is come from? I4. Okay. Therefore, I4 will be selected. I4 will be selected as an output. Okay. So something like this, if you write S0 here, S2 here, LSB first and MSB at the end, you will get only one input only selected. Definitely one input will be selected. Okay. That's not wrong actually. But actually you don't get expected output. The multiplex is working correctly, but you are not getting correct expected output. Therefore, our expected output is first I naught, then I1, I2, I3, I4, something like this. I have to do it. Okay. So therefore, now what is the modification that you can do here? Where should be MSB then? And LSB ఎక్కడ ఇప్పుడు మనకి? So if you keep it like this, for example, S0 here, S3 here. Okay. Then what will happen? The first case is anyway, it's okay. I0 will come. For the second case, I4, I2, I1. How it is I1? I want this one has to come. Okay. As this is this one. Okay. This has to come here. Okay. And if the value of this one is also one has to select it. That means between these two, this should not be selected. This should not be selected. Okay. And here also, anyway, whether it is selected or not doesn't matter. Okay. If it is selected or not, it doesn't matter. It is also not selected. So out of these two things, what it has to go? I1 has to select it. Here I want to have I1, not I4. Even if I write like this also, if I change S3, S1, S0 or something like this, the 0 will be selected. Of course, let me, okay, I'll do one thing. Let us analyze again, okay, by step. Therefore, you can also understand and you can give me the solution for that one also. Okay. Now this S3 is 0. That means 0 is selected, 0 is selected, 0 is selected, 0 is selected. Okay. This is also 0. That means this is 0 is selected. That means out of these three things, this is selected. Here also, what it will be selected? I1 will be, I0 will be selected. Okay. Is it I0 selected or not? I0 will be selected. What it will select here now? I2 will be selected. Here, I4 is selected. Here, I6 will be selected. Okay. Now here, what will happen? I0 will be selected. Here, I4 will be selected. But here, I4 is selected. Out of these two things, since it is one, that's the reason why it is selected. That means I4 is selected. That's also wrong. Okay. Then what we can do? Quickly. Our requirement is that what we have to do? Let's go in opposite direction, opposite way. So I want to select this one. Okay. I1 must be selected. Okay. Then what we have to do? Here, what it should be selected? It can be anything. Okay. Here also can be anything. Can be anything. In this case, what it has to be selected? I1 has to come. Okay. So therefore, Y1 has to come. and this is also I1 has to come. So this must be selected, this must be selected, and but this should be selected here. Okay. So what if something like this I will write 0 0. Let me write here is the 1 0 0. Okay. Forget about what information that you put it here. Forget about that one. Okay. Okay. Now I want to send this I1 to the output side. Okay. Now look at this one. This is one is actually selected. That means this is selected. This is selected. This is selected. This is selected. That means what is I0 for I1, I3, I5, I7. Okay. Since it is 0, what it will be selected? I1 will be selected. Since it is 0, what it is selected? I5 is selected. Since it is 0, what it will selected? I1 is selected. Am I right? I1 is selected. Okay. Now look at this one. Now 0, 0, 1. 0, 0, 1. Now we look at this one. What will happen? This becomes what? I naught. This becomes I2. This becomes I4. This becomes I6. Because this is 1, what will be selected? I2. Because it is 1, what will be selected? I6. Because it is 0, it will select I2. Right? Like this, we have to do it. Okay. So therefore, what is the suggestion that we can keep it here now? It should be MSB. It should be LSB. Okay. That means in the previous case also we have done something like this only. But why we have not get the right answer? Because how we are applying the inputs is important. Are you getting the point? How we are giving the inputs is important. Okay. Therefore, you start with the first position, the first stage, you have to give it LSB. Undoubtedly, we have to give LSB and we have to give MSB. Okay. So therefore, MSB start means that this is how it will start 0, 0, 0, 0, 0, 1, 0, 1, 0, something like this. Okay. You keep it LSB here and MSB, LSB here, MSB here, and start with 0, 0, 0, 0, 0, 1 means that definitely it won't work. Okay. Hopefully, you catch this point, right? Okay. So let me stop discussing how to design this one. Anyway, we got what are the different variables that are required here. That's the reason why when we are writing the test bench also, you have to give the same way. Okay. Right. Okay. Let us go and quickly write this one. Okay. How I have written the multiplexer. Let me go and see what way that I have written the multiplexer. Okay. Of course, I have written only the scalar notation only, not vector notation. But anyway, this is available with us. We are going to talk about how to write by using this one only. Okay. Okay, let me write here. Copy. Paste somewhere here. Okay, shall we start? Please let me know what are the things that I have to write. Module. Okay. Another 10 minutes we can complete it. Okay. Module. Mux underscore 8x1 underscore structural modeling. What are the variables I'm using? I, S, and Y. Okay. These are the three variables I'm using. Out of these three variables, what I'm going to write? Input, What I can write? Let me write 0 to 7 of 5. 0 to 7 of 5. Okay. Uh, okay. Or otherwise, okay, just let's go from higher bit to the lower bit position only. 7 down to 0. MSB is 7, LSB is 0. Okay. Now, this is the one variable. Another variable is input selection line. It is of 3 bit size, 2 down to 0 of S, for example. Next, output is single bit size, Y. Okay. So, how many multiplexers are required for me? Total seven multiplexers. Okay. We take the 7 multiplexers here. Okay. Plus, please remember, you have to remember this one. What is I'm writing here? Look at this. See, this 2 class 1 multiplexer is actually the scalar notation we have used. Okay. For example, okay, accordingly we can write. Okay. So, right, first of all, A is required. Okay. Let me write what is, we have to give, definitely we have to give the name of this particular module. Okay. Therefore, let me call it is M naught. Okay. And A, what is A here now? First variable. Can someone help me? What is the first variable? I of 0, right? Next one is I of 1. Next, S of, what is this? I'm talking about this one. Let me consider this is M naught. This is M naught. This is M1, M2, M3, M4, M5, M6. Okay. What is M naught for M naught having the I naught, I1, and some name let us give. What is the name let us give? For example, T0, for example. Okay. T0, T1, T2, T3, because this is internal to the circuit, right? And this is T4, and this is T5. Okay. There are the 5 nets are required inside of the module, right? Okay. So let me write what is this first M naught. I naught is available. I1 is available. Next, selection. What is the selection here? S of 0. Okay. Now I need to write S of 0. Next, what is the output? T1. So T naught. T naught, this is also I want to write it as a vector notation for the simplicity. T of 0. Did you catch this point, everyone? Please let me know. Is it clear to everyone? Okay. Just simply whatever the structure that is there, according to the structure I have written. Okay. Since whatever the module that I have called, it is used in the vector notation, scalar notation. That's the reason why, even though I have written the main module in the vector notation, I have taken the individual variables, something like this, scalar form that I have written. For example, so whatever I have declared previously, the 2 plus 1 multiplexer also something like this, for example. This is also, for example, 2 bit size I, it is a S, and it is Y. Please let me know how to write this particular statement, how this statement will modify. So something like this I have written. Okay, therefore this is actually a module. Okay, mux underscore 2 class 1. Okay, instead of it, I have written, yes, I have written, Y I have written. This is the way I have written. Assume that the vector notation I have used in the 2 cross 1 itself. Then I'm calling this one. Then how can I give this way? If I call this particular one, how can I write? Mux underscore 2 cross 1. This is M naught, for example. Then what is this one? I of L or I, L. I of 1 down to 0 of and this is S of 0, and this is T of 0. Did you catch this point? Here actually 2 bits that we are writing in the vector notation. Why? Because we have I is actually 2 bit size inside of it. Okay, what we would have written here, the input is 1 down to 0 of I have written in this way, and another input is S, and output is Y. So you can see this is the vector notation I'm using. That's the reason why I have to write the vector notation only. I have to write here. Did you catch this point or not? Okay. Yes. Okay. So because since I have written previously the scalar notation, I'm using the scalar notation approach only. Okay. So just I'm going to remove this one. Okay. So if I don't want to remove this one, what I can do? Without remove this particular statement, I want to keep it like this, but does not have any impact. Make that as a comment. Okay. Just we have to use the 2 forward slashes. It become a comment. Okay. So anyway, so we are going to take this particular component how many times? 8 times that I have to consider. Another 6 times. 1, 2, 3, 4, 5, 6, and 7 is already available. Okay, there's a 2 plus 1 multiplexers only. Just I have to modify these things. Okay, so therefore this is 1, this is 2, this is 3, this is 4, this is 5. 6 is also right. Okay, 1 is already available, right? I'm so sorry. I want to change this one to M1, M2, M3, M4, M5, M6. Okay, na? Okay. Now look at this particular one. So I don't want these particular things. Okay. All these things will changes according to the inputs and outputs. Can you somebody help me what I can write here? Please let me know what should I write for M1. Sorry, for M. Okay, this is also for M1. What I have to write? What is the hardware for M1? M1, I2, I3. Selection line is S0. Output is T1. Output is T1. Okay, this is I2, I3, S0, T1. Okay. Similarly, what about the M2? Of course, we can write it very easily that 4, 5. This is 6, 7. Okay. First is multiplexers are completed. What about this one? 0, 0. This is 2, 3. Hopefully that is completed. Now we are going to talk about the second stage. M4 is available at the second stage. M4, what is the first variable? T0, T1. Okay, T0, T1 is required, not I. Just we want to remove the I portion. Okay, as this is T0, T1. Next, this is S1, T4, for example. 0, 1, T, T. Okay, next. What about M5? T2, T3. Very good. Next, what about this one? 1. This is T5. What about the last one? Very good. T4, T5, S, S2, Y. Right. Very good. It is y. So therefore, we need to end this module, something like this. So we cleared every aspect. Anything we missed here? Y. Okay. So we need to write y. What is the size of the y? 5 down to 0, right? T5 or quadamano. So T5 to 0 of 3. Right. Very good. Okay. Now, okay. Just I want to take two by four decoder as a assignment. Okay. Please do it 3 by 8 decoder by the 2 by 4 decoder. Okay. And do you know how to write the test case for this 4-bit adder? You know, if you are talking about the 4-bit adder, how many combinations I should apply in general? How many combinations I should apply? For 1-bit adder, how many combinations we have applied? 8 combinations we applied. A, B, C, A, N, 0, 0s to 1, 1, 1. 8 combinations we have applied. But for the 4-bit adder, how many input combinations I should apply? 2 power 9. 2 power 9 combinations we need to apply. It's very difficult actually for us. Okay, we can apply only 5 or 6 combinations. We want to verify that one. Okay, so for that is the reason why I'm going to write the test bench for the forecast for the 4-bit adder. You can write the test bench for the 8-cluster multiplexer. Okay, I will go and write the test bench for the 4-bit adder. Test bench. Okay, so quickly let me write what is this module. Module adder underscore 4-bit underscore test. Okay, what are the variables here? Reg. What are the inputs here? What is the size? 3 down to 0 of A comma B and another reg. Okay, it's not only single bit size, right? CAN, the wire, 3 down to 0 of S. Next, another wire, C out. What is the name of this module we would like to test? This is the name of the module we would like to test. We take that copy. Let us give this M0. Okay. Now initial block. Initial. Okay. Let's begin. Okay. What is the component I have to give? What should I write here? First, I need to write, okay, A is a 4-bit size, right? If A is equal to 4-bit of 0, 0, 0, 1, and B is equal to 4-bit of 1, 0, 0, 1, okay, not 1, for example, something like this, 0, and CN is equal to 0, for example. What output that you can expect? This is one combination I have given. Okay, first is 1, and that is 8, 1 plus 8, 9. 9 has to produce an output. Cn is already 0, therefore 9 is only the output. Okay, so what is the expected output here? You can see sum is 1, 0, 0, 1. Okay, and Cout is 0. It is not sum actually, it is yes. This is what the output that you have to expect. Okay, this is the 1, and that is 8. 8 plus 1, 9. Sum is 9, carry is 0. Some take another input. Okay, some other input. For example, A is equal to 4 bit of 1100. Okay. B is equal to 4 bit of 0010, and Cn is equal to 1. Then what should be the expected output? Can anyone? What is this? It is actually 12, right? 12 plus 2, 14. 14 plus 1, 14 plus 1, 15. Am I right? You can see here 1100, 0010. Here is a 1. This is a 1111. This is a 15. Okay. So therefore S should be 1111 and CO should be 0. Okay. Now, for example, take another one. We want to show the carry information also. A is equal to 4 bit of 1111 and B is equal to 4 bit of 1011 and Cn is equal to 1, for example. Then what should be the expected output? 1111, 10111, 1. What is the expected output? It is the 1 and 1. It is the 1 and 1. Here is the 0 and 1. Here is 1 and 1. Okay. Therefore, sum is actually 1011. C out is 1. Okay. Therefore, that's enough actually. But please try some other combinations also. Okay. Of course, we want to use some, for example, 10 nano. You can write it here. Here also, let us take the 10 nano. Another 10 nano. I want to stop the simulation. Another 10 nano. Dollar stop. Dollar stop the simulation. Okay. That means at 30 nanoseconds, we want to stop the simulation. Finally, end module. Okay. So this is how we need to write the test bench for the 4-bit adder. Therefore, if the number of inputs are more and more, definitely we cannot give exhaustively the number of inputs here like this. Exhaustively we cannot give. That's the reason why we can give some important test patterns that we can give. Okay, I am assuming that these are the important ones, but actually you can give wisely that how can I apply the input signals. Okay. So as the number of inputs are increases, writing the test bench is not advantageous. That's the reason why people have gone for the system verilog approach. Okay, there we can apply more number of input to test that particular logic effectively. Okay, this is the one constraint there with the verilog. Okay, we stop here. Okay, please try to write the test bench for the multiplexer and write the structural modeling for the 3-way decoder and its test bench also. Okay.